Welcome back, everybody. We're going to continue our discussion of carboxylic acids with a reaction we've seen something very similar to before. Thionyl chloride. In chapter 10, we saw thionyl chloride react with an alcohol SOCl2 and pyridine, and the alcohol got converted to an alkyl chloride. The same result is observed here with the hydroxyl being replaced by a chloride. The mechanism is almost identical, except the fact that we're not starting with an alcohol, we're starting with a much more acidic species. Remember, an alcohol is a trillion times less acidic with a pKa of 17 than is a carboxylic acid with a pKa of 5. 17 minus 5 is 12. 10 to the power of 12 is a trillion. So to not acknowledge the fact that your acid is more acidic and you should react it first is to not say you're understanding pKa's. So please prove you understand pKa's and start this mechanism with the acid-base step, and don't mess up and start this mechanism with the acid-base step, because you can't deprotonate an alcohol with a weak base like pyridine. You can deprotonate a carboxylic acid with a weak base like pyridine. There's even a comment here about the order being changed. After that, the mechanism goes pretty smoothly. We have the carboxylate as a nucleophile attacking the very positive sulfur. Why is sulfur so very positive? It has 4 bonds to more electronegative atoms. Why does the pi break before the sigma? Pi bonds are roughly 60% the strength of a sigma. If you have to choose between breaking a pi or a sigma, you always choose pi. And then after you make an O- in step 1, the gray step is second. It eliminates Cl-. And then we have chloride, usually a fairly poor nucleophile. It helps that you're generating a gas molecule. This is our second generation of a gas molecule today. I don't think we've had a day with double gas molecule regeneration. So mark that on your calendar. It's the first time. And this happens to make SO2. You could argue, and this would be a great argument, and I'd be very happy to see this on a test. Here I could say green second and gray third. Do I have a gray with my starboard? I think I do, yes. Remember what I just said? If you have a choice of breaking a sigma or a pi, you should break the pi first. Green says, where am I here? They're going to break this. Yeah, this would be the second step also. And then gray third would be the lone pair coming back. And we need our gray. Is it going to show up? Oh, it's almost invisible. I don't have a darker gray there. Sorry. So the reason I left it like this is you did learn in chapter 10 to do it this way without the green and gray combination. I will still accept that. In fact, if I go back here, I will still accept if you don't break this down If you don't protonate first and then you just do the elimination like you saw in chapter 10, then that would be fine. If you can use previous mechanism from the textbook, then you have a good argument. The teacher accepted it then, he should accept it now, and your argument will stand. I believe this mechanism is straightforward enough that we don't have to do another example. We have the option straight from the book is fine, or with the slight modifications here, also fine. Once again, there's a gray arrow from here to here you might not be able to see. And moving on to reduction. Remember, reduction is moving electrons closer to an atom. So the opposite of oxidation, yes. And reduction, I hope this illustrates that reduction of carboxylic acids is difficult. None of these reactions works. And even the one that does do a reaction, that is not a reduction. It's a simple acid-base reaction with this amine type base taking the H off. So the only way we can successfully do a reduction of a carboxylic acid is by using lithium aluminum hydride, followed by step 2 with hydrochloric acid. And there is the overall result. And yes, you replace 2 bonds to oxygen, 2 bonds to oxygen with 2 bonds to less electronegative atoms, hydrogen. The electrons got closer to this carbon right here. That is a reduction. Mechanism is similar to the lithium aluminum hydride reduction you've used before with aldehydes and ketones, but there's more to it. First step is always generation of the hydride ion. This is not to be thought of as the same as a hydride base. It reacts more like a nucleophile. In this case, it is being a base because you have an acid that's fairly strong. The hydride cannot ignore that. Even though its typical nature for this generation of hydride is to be a nucleophile, here you've got to do the acid base first. So yep, you're going to be using excess lithium aluminum hydride. Hydride now attacks the carbonyl, and you could generate an O-, but you're going to need this O- to leave, and I don't want it leaving as O2-. So make a bond to this very positive aluminum here. That's a little different than we've seen before. And we will do our own version of this mechanism underneath because it's got some changes. Here your hydride's doing what normal hydride does from lithium aluminum hydride, attacking a carbonyl. And then hydride leaves because aluminum's back to being an anion, just like it was at the beginning. In fact, it's much more anionic here than over here, and that means it's a less stable metal. Anionic metals are very unstable. That's just their nature. So this H- is hopping off even before the second molecule of this reacts. And then you eliminate the O- leaving group. And there's the O- leaving group. Truth be told, the O- leaving group, when you do the final step with HCl, I didn't show it. You don't need to show me either. There's an excess of HCl. It will protonate to make HOALH2, which isn't even the final product because each of these hydrides reacts as well. We won't get into that. But the most important thing for HCl is to protonate the conjugate base of the alcohol to make the alcohol. Why is it a primary alcohol? Well, I'm going to argue it doesn't have to be primary alcohol. If R was an H here, I'm going to write down unless R equals H. If R is equal to H, you have methyl alcohol, which is less than primary. All other alcohols will be primary, except for that one exception. And why do we have 2 new H's? Well, the first new H was attacking the carbonyl here. After elimination here, I didn't point it out, but look, there's an aldehyde. We saw what happened to aldehydes in the presence of the same chemical in chapter 16. They reduced to alcohols, primary alcohols. And there's your second mole of H minus reacting. Third mole if you're counting. Sorry, I keep forgetting. First mole, it did an acid base. Number one. Second mole, it did a carbonyl attack. Third mole, it did another carbonyl attack, this time on an aldehyde. So let's do our own version of this mechanism right here. Let's go with benzoic acid. Forgot what chapter I was in. Benzoic acid. And HCl. You're going to get benzyl alcohol. So there you go. Do our own version of this one. Oh. Clearly I hit Control T by mistake. Okay. What is the first step up there? We see it. Generate H minus. Just happy to see, I think almost everybody did this on the test. Generate H minus right here. H minus is a base first. Carboxylic acid. Base. Generating a carboxylate, which we're going to attack. Short form for phenyl. If you're curious, the other product was H2. I don't believe I showed that either. H2. And now the second hydride. Yes, there's an excess here. Excess HCl is understood. Second H minus does this. There's an aluminum chloride you generated back here. Aluminum chloride, AlH3. Its name is alane. Sounds very French. It will, AlH3 will be picked up by the oxygen by breaking the pi bond and making a sigma bond to the oxygen. So we're going to break the pi bond and make a sigma bond to AlH3. Same step. Phenyl, OAlH3. Back to being a minus. O minus. Keeping score, you got a new H. And now, we could have combined two steps, but since we've drawn the intermediate a little late, I could have used a lone pair here and resonated this thing off, this whole thing. Right here, I could have combined this with this coming back and kicking off this species here. Or I can do it this way. Just break it down to steps. Two species, That's an R. Phenyl's the R. AlH2 with an O minus. H minus, number 3. It's going to attack the carbonyl. There we go. There's your second H. HCl is going to make that species into our product. HCl is also going to make this species into our product. HCl here. HCl here. Pick up a proton. Pick up a proton. Generating your primary alcohol and side product, which I really don't care about the side product. And there you have it. Nice way to make a primary alcohol. It's not a great description. I mean, it's more accurate to call it a benzyl alcohol, as both its name and a category. And that's the end of lithium aluminum hydride reduction of carboxylic acids. And it brings us to this, which is what I want to be. Let's see, what do we got next? Yeah, we'll finish a short segment with that one. We'll do this segment right now. We're going to look a little more at the acidity of carboxylic acids and break it down. This is very close to 5, as we've learned. That's our prediction, 5. We see some other 5s on here. Close, but a little lower. They're all 5, but a little lower, aren't they? Why would 2-chlorobutanoic acid be less than 5? And it's pretty substantial. So 2 units, almost 100 times more acidic. And the answer to that question is not why does the chlorine make this more or less stable. The answer to the question has to be based on stabilizing the conjugate base's stability. And that is called the inductive effect. We first saw the inductive effect when? It's been so long. It's been so long. It was chapter 4 when we studied acids and bases. How appropriate. It also covers a lot of things like mechanisms and other such organic chemistry nuances. So the inductive effect says by having an electronegative chlorine here with a dipole in that bond, it induces a dipole. So induced dipoles will be in baby blue. Induced dipole caused by the first dipole. It's going to pull electrons towards the carbon as it develops a positive charge. And it's going to pull the minus charge closer to the nucleus here, closer to the oxygen's nucleus, which is a good thing. If you can pull a minus charge closer to a nucleus, you've made it more stable. If you can make it more stable, then you're going to make more of it because it's easier to make. That's why we made a lot more of these carboxylates here than under the same conditions making these into carboxylates. And what about moving the chlorine over one more? Why is the effect less substantial? But there's an effect, isn't there? 4.8 to 4.1 is not a zero change. Well, the inductive effect is sensitive to how many bonds you have to induce, and it diminishes. Notice this little blue and caused by this big dark blue is smaller and even smaller yet. Once again, these are not bond dipoles, they're induced dipoles by this first dipole. And it's diminished over more distance. There's proof. And what about this one? And more inductive effects. That's a cation there. That has an even more profound effect. It's not about electronegativities. It's about positive charge. That definitely induces a dipole. And then that's a bigger dipole. How do I know it's a bigger dipole? Well, this number here is smaller than this number. Means this acid's stronger. Alanine's pKa 2.3. And then we won't do this next one because there seems to be a new number showing up here. Isn't it surprising that the N plus is a bigger inductive effect than a neutral oxygen? Based on strictly electronegativities, you wouldn't make that prediction, but the cation has just as big an effect. This is not a cation. So all those ones are for inductive effects. 2 is a hybridization effect as well. If I can generate this from pyruvic acid, we have next door, carbonyl, yeah. No, I didn't draw the molecule. I drew acetic acid. Shame on me. There is pyruvate, which is what pyruvic acid looks like in biology anyway. And pyruvate has an sp2 hybridized carbon next door. I want to remind you that's 33% S. Pulls minus closer to nucleus than sp3. Which is 25% S. Where did I come up with 33 and 25? Did you forget? I've got a hybrid whose name has 3 pieces. SPP, SP2. One of those is S. That's 1 out of 3, 33%. If I had an SP3 hybrid, like on every other carbon that's been in the alpha position so far, SP3, 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 SP3. SP3, 4 fingers, S, 3 Ps, 1 part S, 4 parts total, 25% S. So I like SP2 on the alpha position better than SP3 because it stabilizes the anion that I'm making. It's pretty substantial, isn't it? Why did I put 1 and 2 here? Well, not only is it an SP2 carbon like it is here, this would be strictly the hybridization effect, but it's also got an electronegative oxygen there causing an inductive effect. That's why this acid is stronger than this one. It's got both things going on. Okay. What do we got here? Let's look at a series of benzoic acids to conclude this segment here. We have normal benzoic acid. No monkey business, just the benzenes. Why is it 4.2 and not 4.8? We got an sp2 hybridized carbon. That's called a hybridization effect. All right, that's cleared up. Why did this go down to 3.3? Well, we got the hybridization effect and the inductive effect of a fluorine. Moving the fluorine further away, lower inductive effect. Moving the fluorine even further away, very little effect. Okay. And what's better, a SP with a 50% S or an SP2 with a 33% S? 50 beats 33. It looks pretty substantial too. Isn't this our lowest pKa on the page? Yeah. And we got one finishing molecule here. Cl3C. And before we come back, why don't you Google the pKa of trichloroacetic acid. And it's got a triple inductive effect that makes it much less than 5. And we will pick up after the break with our final segment in chapter 17. Oh,